Okay, great. Okay, so thank you for the invitation to give this talk, firstly. I'm really excited to be here at HEFT and to be able to share with you the results of our recent Top-Higgs Diboson and Electroweak fit to the standard model effective field theory. So all of the results I'll show you are based on some recent work with Jan Ellis, Ken Mamasu, Veronica Sands, and Tavang Yu. They were all produced using a code called FitMaker, which I'll mention briefly at the end. But first, let me focus more on the global fit itself. Sorry. So we'll start with the SMEFT, the standard model effective field theory. So by now, this is really well established as a powerful tool for capturing deviations from the standard model and generally for performing indirect searches for new physics. One of the really key features of it is that it's model independent. So we can remain agnostic as to what kind of new physics is out there, as long as we just assume that this new physics is heavy. So it sits at some scale lambda, larger than the scale of our experiment. And with this assumption, this allows us to parameterize the effects of the new physics just by supplementing the standard model Lagrangian by a series of operators suppressed by this new physics scale lambda squared. By writing it in this way, I'm assuming that we're going to restrict to dimension 6 throughout this talk and throughout our fit. Okay, so the price we pay for this model independence is that we get a huge number of operators. We're going to work in the Warsaw basis, which is what I'm showing you here, all of the operators from the Warsaw basis. And what I really want you to just get from this table is just that there's a huge number of different types of interactions that interlink all of the different sectors of this of the standard model. So we have interactions of Higgs and gauge bosons, Higgs and fermions, fermion-fermion interactions, all possible different interlinking interactions. And so this SMEFT is a really tight theoretical framework which links all of these different sectors. And so it's no surprise that we can see that each operator contributes to multiple different types of data sets. And so we can expect some sort of interplay between the different sectors of measurements from things like Diboson measurements, Higgs measurements, top, Electroweak measurements. And the example I'm showing you here comes from our fit, where we look at how the different operators we use in the fit contribute to the different types of data sets. So if we start with the Diboson sector, we show that this will constrain things like the CW, the triple gauge operator, as well as some of these bosonic and fermionic interactions. But most of those operators are also constrained by Electroweak precision observables. And similarly, a similar set will be constrained by the Higgs, as well as these Higgs-only operators, and some of these were fermion operators, and the CG down here. And then as more top data becomes available, this starts to constrain those similar operators too, as well as top TT bar plus vector bosons. And then we also have constraints coming in from top Electroweak, so things like single top. And so you can see that almost none of these different sectors are distinct from each other. They're all contributing to overlapping data sets. And so this really highlights the need for a global fit, combining multiple different data sets at the same time in order to really pin down the types of deviations that are allowed, as well as the types of correlations allowed between the operators. And so our work is just taking a small step in this direction. We include top Diboson, Higgs, and Electroweak precision observables in a fit to 34 of the Warsaw basis operators. So this is the 34 operators shown here. The way we decide on these operators from that full table of Warsaw basis operators I showed you before is by making a few assumptions. Firstly, we neglect any CP violating operators, and we impose two flavor scenarios. Either we work in the flavor universal scenario, so SE3 to the fifth, or we relax this slightly, singling out the top couplings. So we relax this SE3 to the fifth to an SE2 squared times SE3 cubed. So this removes the top doublet and top singlet from these, it's no longer forced to respect these symmetries. And so this will allow operators such as the OTW, OTB operators, some of these four fermion operators that would be nicely constrained by top data. This symmetry is laid out in more detail in this reference here. And then in both of these flavor scenarios, we also include four Yukawa operators. So the tau, the mu, the B, and the top Yukawa are also included. Again, these both break these flavor assumptions, but these are all operators that would be expected to be constrained by the Higgs data we have. And then one last thing to mention about conventions is just that we always normalize the operators by a factor of C over lambda squared, even in the case of the Yukawas. So we never have a factor of the Yukawa in front of those operators. Okay, so on the side of measurements, I mentioned that we have these four categories. There's Higgs, top, Diboson, and Electroweak. They comprise a total of 341 statistically independent measurements. We make sure to avoid choosing any statistically overlapping measurements, and we include all the correlation information we can from the different published covariance matrices. And so I just wanted to give you a quick breakdown of how these measurements are, how they compose that full set. So first, We have the Higgs, there's 72 of these. Most of these are signal strength combinations from either the LHC Run 1 or Run 2 CMS combination. We also have this really large simplified template cross-section combination from Atlas at Run 2. This was one of the highlights where they combine their data into a total of 21 simplified template cross-section bins and also provide this published covariance matrix. So this provides a huge amount of differential information about the Higgs production. And it's really easy for us to use. We are much less likely to make mistakes as theorists using this experimental data. So this is a wonderful resource. As well as Higgs to Z gamma and Higgs to mu mu signal strengths in the Higgs sector. And then moving on to the Electroweak, we have 14 of these from LEP, Tevatron, and the LHC. And these are all measurements of things like forward-backward asymmetries, W mass measurements, Z pole measurements. The Diboson sector has 118, and these are things like WW, WZ production, and also ZJJ angular distributions, which were included to try and drive the sensitivity to the OW operator, that WWW interaction. And we'll see the impact of that in a few slides. And then finally, we have top measurements from the LHC, things like TT bar production, TT bar plus vector bosons, and single top. So with this data and our theory conventions, we can then start to combine them into a fit. Most of the results I'll show you come from a simple least squares fit. So we're fitting these Wilson coefficients by minimizing a chi-squared. We do this by constructing just a vector of observables, y, with covariance matrix v, and we incorporate all of our predictions into a vector mu. So for every element of y, we have an element of mu. And this can be expressed in terms of the standard model piece plus this matrix times the Wilson coefficient. So we are restricting to leading order in the EFT expansion. And so that's one of the downfalls of this method, that we can't go to higher order in the EFT expansion. But what we lose in that restriction, we gain in the fact that this is an analytic method. We can solve analytically for this best fit Wilson coefficient as well as the covariance matrix. So they're just given by this expression here. The covariance matrix is just the inverse of the Fisher information. And this makes this method quite quick to use. We can redo the fit with different types of data sets or in different subsets of operators, which is a useful way of assessing the impact of different data sets and how the fit looks, for example, for specific UV models. So moving on to some of the results. First, I'll show you a fit in the flavor universal scenario. So this is that SE3 to the 5th symmetry, which leaves us with a set of just 20 operators. So these are these operators shown here on the x-axis. And we're using just the Higgs, Diboson, and Electroweak data in this fit. And the main result is that in red, so we're looking at the full set of 2020 data. This is the data I showed you a few slides ago. And these results are the marginalized results at 95% confidence level. And there's two interesting comparisons I'll make here. So the first is just comparing between the red and the brown. And this is what happens when we remove the ZJJ angular distributions from the fit. And you can see there that the sensitivity to that OW operator is lost. So this ZJJ, we're not completely lost, but it's reduced. And so this kind of confirms that this ZJJ measurement is driving the sensitivity to that operator there. A second interesting comparison is what happens when we remove the simplified template cross-section data. So between the red and the orange, you can see that in most cases, the constraints widen slightly. So going from red to orange, but in a few, the constraints widen hugely. So this is a huge change between red and orange here for things like CHG, CG, and CTH. And this is because the simplified template cross-section measurements are really important for, in particular, the gluon fusion bins. These are really important for improving the sensitivity to these operators in particular, as well as breaking the degeneracy between them. And we can see this by looking at how the predictions for the gluon fusion cross-sections, how they depend on each of these different SMEFT operators. So first, if we just focus on this square here, this is the zero jet cross-section, which matches up nicely with the signal strength. So if we just had signal strength measurements, we just have this bin. It depends on 4 of these operators. There's no sensitivity to CG, and we would have a degeneracy between these 4. So by instead including all of these different bins, we see that not only do we increase the sensitivity to the operators, for example, especially in this high PT bin, but also the degeneracy is broken. And so it isn't surprising that we improve sensitivity to those operators in particular when we go from no STXS to including STXS. So then moving to the full fit, the fit in red here is the full 34 operators under that top specific flavor scenario and fit using the 4 different categories of data, the Electroweak, Diboson, Higgs, and Top. And again, these are the marginalized results, so allowing all of these operators to vary simultaneously in the fit. Down here, we're interpreting this fit instead in terms of sensitivity, so the scale to which we're sensitive. And this is shown in 3 different scenarios, either Wilson coefficient equal to 1 or a strongly and weakly coupled 4 pi squared or 0.01. So this leads to these 3 different heights of the histograms. We're also comparing the main fit, the full fit in red, to 2 different subfits, either in left and orange, where we look at this flavor universal scenario constrained by everything except the top data. So this is similar to the fit I showed you 2 slides ago. That's in orange on the left. And then in pink on the right, we have top related operators constrained by top data, as well as Electroweak data. And so the point of this is really just to show how each of these subfits changes when we go to the full fit. And you can see the shift isn't huge. We have, for example, the red or the orange and the red here are quite similar. The pink and the red here are similar, but there is some movement when we allow all operators to vary simultaneously and when we include the full data set, especially, for example, here you can see there's a change and there's some change here. And so it suggests that there is some interplay between the sectors. As we gather more data, these 2 sectors are starting to really talk to each other. We can analyze this interplay in a bit more detail by looking at the operators relevant to Top and Higgs data in particular. And so what we're looking at here is the constraints on the operators OTH, OTG, OG, and OHG, projecting onto each of the relevant 2D planes. Also marginalizing over these Higgs specific operators, and in some cases, the 4 fermion top operators. And what we're looking at here is what happens as we include more and more data. So we start with the yellow, the Higgs data only without TTH. And so most of these constraints are driven by things like gluon fusion. So we see we have these large constraints, a large correlation here. And then including TTH really pulls us down to these green ellipses, but really incorporating all of the top data shrinks the ellipses greatly down to these small purple ellipses. And so this really just kind of shows that there is some interplay between the sectors, and that we do need to include more, all of the data available to really pin down these operators. So another way of analyzing this full fit is looking at the principal component analysis. So this is a fun plot to get lost in, really. We have all of these operators down on the y-axis. And what we're showing vertically in each column is the eigenvectors of the covariance matrix. So for example, this left column here is an eigenvector of the covariance matrix, and the composition involves CHB, CHW, CHG, and CHWB. Similarly, this rightmost one is composed completely of CTB. Up here, again, we're showing the sensitivity in terms of scale, and then each of these columns shows the constraining power of the various different data sets. So this one I talked about, the leftmost one, is mostly constrained by Higgs measurements, simplified template cross sections, we have signal strengths, and a small component coming from Electroweak precision observables. And so this is quite useful for diagnosing where the constraints are coming from, which data sets are most relevant, and what kind of impact they're having. So then before I finish, I'll just talk briefly about UV models, because after performing this SMEFT, we really want to know what this means for physics beyond the standard model and what this means for UV completions of the SMEFT. And so we try and analyze our SMEFT our fit in terms of some BSM benchmark models coming from these 2 references here. In particular, this one provides a tree-level dictionary, which matches each of these benchmark models to the dimension 6 operators. So we can interpret these operators in terms of couplings of these single field extensions. And this table is just showing all of the different types of model single field extensions of the standard model included in this analysis. So I'll just highlight a few. We have, for example, S, which is a spin 0 boson standard model singlet. Similarly, there's N here, which is a fermion standard model singlet. So that could be like a right-handed neutrino. Things like B and W here, they are sometimes called like a Z prime or a W prime. And similarly over here, we have fermions with various different SU3 charges and SU2 charges, some colored fermions here. And so all different avenues for model building throughout this table. And so as well as analyzing those and placing constraints on their couplings individually within the paper, we also look at the patterns that emerge when we integrate out these operators. So what is common between the operators is that when they're integrated out, generally they, what's common among the models is that when we integrate them out, they generally generate similar sets of operators. So if we pause and look at models with couplings to leptons, these are things like NE, the deltas and the sigmas. So if we go back, we have N and E are fermions, and these deltas and sigmas are fermions again with different sc2 charges. What these have in common is that they all feature some sort of couplings to leptons. And so when they're integrated out, they generate operators, of course, involving leptons, as well as some sort of other interactions. And what's common is that generally we find that because these are all linked by a single coupling of the models, the operators and the Wilson coefficients will be proportional to each other. So CHL1 is generally proportional to CHL3, and CLL will be proportional to CHE. And so in order to look at what a fit means for these kind of patterns, we analyze the fit, reperform the fit in the subset of operators relevant to these kind of models. So here we're looking at the constraints in the plane CHE versus CHL1. And the yellow ellipse shows what happens when we constrain those operators when marginalizing over CLL and CHL3. So this yellow ellipse here. And then similarly, when we set CLL equal to 0, the constraints shrink slightly, and we get this green ellipse here. And so this is really just a guide for models of this type. Generally, we'd expect them to fit somewhere within these kind of constraints. And we kind of reinforce this by showing how each of these single field extensions sits across the ellipses shown here. So for example, these two delta models, they feature most of these operators equal to 0, and we find that they kind of sit, by projecting the constraints of those models onto this ellipse, the constraint sits here. And similarly, each of these with CHL3 proportional to CHL1, we find generally sit along this kind of line here. And so a similar model, maybe slightly more complicated, featuring similar patterns, would generally follow the same type of constraints. And so it's a useful kind of guide, I guess, to the type of constraints applied to models in these kind of situations. And we can see, if you look at the paper, I'd recommend looking there for similar cases where we have more quark-related operators, third-generation operators, and boson-specific cases as well. So with that, I'll conclude and just mention that all of the results I've shown you were produced using a code called FitMaker. So this is a publicly available Python code. You can get it from GitLab at this reference here. It's all there and all online, but the version for public use is still to come. So we will have more documentation available soon. And generally, the goal of FitMaker is to provide a fitting framework which is adaptable, flexible, and extensible for performing global SMEFT fits, and generally for statistical inference and BSM physics. It's flexible in that it's built in this nice modular fashion so that the user can easily expand it with additional models, additional data sets, and hopefully we'll continue to expand it going forward as well. So that's everything I have to say then. Thank you for listening.
Thanks, Maeve. So any questions for Maeve? From the room first, actually. Yes, looks like we have one.
Hello?
Hi.
Can you hear me?
Yeah.
Hi, this is Jiayin Gu. So very nice talk. Could you go back to maybe either page 12 or 14?
Sure. So 12 here, yeah.
Yeah, I mean, maybe you mentioned there already, but for the plot at the bottom, so why does the bound depend on the coupling?
Oh, so generally when we constrain in the EFT, we're constraining the factor of C over lambda squared. And so in each of these, we assume a value of lambda. So the constraints we place on these, we're assuming a value of lambda equals to 1 TeV. So when we constrain that factor, sorry. So
go ahead.
Sorry, were you going to add something?
Yeah, I was saying that, but the label on on the left hand side is already the combination, right?
Yeah, so we constrain this combination, and then if we, for example, here if we'd like to interpret the constraints in terms of C, we need to pick a value of lambda, or here if we want to interpret these in terms of lambda, we pick a value of C. I guess I see what you mean. So this should really, yeah, okay. So I guess this label should be CI equal to CI constant. And here we've got the 3 types of constants. I don't know if that cleared up a little bit more.
I was wondering maybe, I mean, you made some cuts on like whether you throw out the events with very high energy, and that can depend on the coupling. I don't know if that could be the case.
For this plot here?
Yeah, yeah.
So here it's just a really rescaling of the constraints depending on the different coefficients.
Okay, thanks.
Yeah, maybe the label is actually a bit
yeah,
confusing
I agree
now
that that's a
I
bit.
think about it.
Yeah.
Thanks for that, Jane. We might have to update the label.
We have another question.
Go ahead.
Hello. Can you hear me?
Yep.
Yeah. I want to ask why do you neglect the CP validating operators in your
yeah,
fitting?
you mentioned that. So yeah, I discussed that in the beginning. So we neglect those really because we don't expect them to be constrained by the fit that we're doing. So we're fitting linearly in the Wilson coefficients, and so most of the observables we're looking at won't constrain any CP violating operators.
Okay, thank you.
Okay, we have another question.
Okay.
Hello. Hi, Maeve. I have a simple question. Can you hear me?
Yeah.
Okay. So do we actually know the maximum energy scale of the experimental data that actually goes into your fit? Because that would be useful for estimating the validity of the effective field theory when you apply the limits to some concrete models.
That's a good point. I actually don't know it off the top of my head. I don't know, Ken, do you remember that scale?
Depends a bit on which sector of measurements.
Yeah.
So for the Higgs, it's not that high. You know, it's these STXS bins. I think you can see it in that plot that Maeve has on the STXS.
Here. Yeah, so about 200 GeV
Yeah.
there.
Whilst TT bar goes up to maybe 1 TeV or so in invariant mass, sometimes a bit higher.
But the highest bin is PT larger than something, right? So there's no upper bound.
True, there's also no upper bound, but so there's an interplay with energy scale and which energy scale is the maximum of, and also which energy scale is actually driving your sensitivity.
Right.
So I agree that it's a non-trivial thing to actually check, which we didn't do in detail, and that would be something to look into actually.
But I think for our models, the constraints driving the model fit, none of it is really affected by the high energy data.
That was Tival, by the way, I think. Hi, Tival. Okay, yeah, so for the explicit model interpretation, you mean?
Yeah, I think if we actually remove all the, let's say, PT above 500 GeV from our data set, I think nothing would change that much apart from maybe CW and things like that.
Yeah, it's quite possible, but I guess it's something which would be interesting to try and quantify in general.
Yeah, definitely.
Thank you.
Okay, unless we have any urgent questions, I would propose that we keep going. Oh, actually, there is a hand. Oh, it's Mike. Okay, let's go with Mike, and then we'll move on to the next talk.
So just a quick question. Could you comment on the use of marginalization over profiling here? And if you check to see if the marginalization and your choice of the marginalization had any significant impact on the constraints that you found?
Yeah, so I guess in this case, because we're working with this simple chi-squared case, this is a chi-squared, which is a simple Gaussian. So the profiling and the marginalization coincide in this fitting. And so there isn't really a distinction between them. I don't know, does that answer the question?
Well, because usually people think that there's a distinction if there's flat directions of how the marginalization can come in to break a flat direction by the prior versus profiling, which tends to pick up the flat direction. So you're saying that that doesn't happen? Because usually people think there's a distinction there.
I have to think about this more. I think even when you speak about a prior, that's more of a Bayesian interpretation. So I'm not sure how that comes into this. So this is really just treating.
Well, I guess what I could say, taking interpretation issues out of it, does your statement of the equivalence hold if there are flat directions, pure flat directions?
No, probably not.
Okay.
Yeah,
I think
no.
there's a distinction there.
Yeah, okay, that does make sense. Yeah, I'll have to think about that more, but yeah, you're right there.
Okay.
Yeah, I think the simplicity of this framework means that if there's a flat direction, you don't get a fit. So you don't get a result. So
yeah, so I think the thing is, because of that, it's then the combination that lifts the flat direction, right? And then what's lifting it is kind of whatever breaks it, but then even if that's like kind of not so strongly constraining, it's whatever breaks the flat direction leads to the constraint. And so then you worry that if that's what's breaking it in one case versus the marginalization choice, which can also break it, that you can actually have an impact on the conclusions.
that's a good point. Yeah, actually, I remember there was a paper by Chris Murphy who proposed a way of doing it in the profiling way by introducing these regulators in the chi-squared, which are the equivalent to using a prior. So that's something we could use to check out to where these directions are.
Yeah, that would be interesting.
Okay, great. I think in the interest of staying slightly ahead of schedule, we should thank Maeve one more time and then move on to the next talk. So next we have